Single text prompts are effective for individual assets, but production-scale media requires thousands of consistent clips, a volume that breaks manual pipelines. Relying on a human in the loop for evaluation creates a static roadblock. Production volume inevitably outpaces the speed of manual inspection. Large language models excel at processing discrete text tokens, but struggle with the high-dimensional, continuous perceptual data found in images and video. Standard pipelines often collapse when tasked with these complex media formats. Replacing the human prompt engineer with an autonomous multi-agent pipeline governed by strict data contracts allows for enterprise-level scaling. The objective is a stateful generation agent that functions independently, evaluating its own performance to ensure continuous output. Google's Agent Development Kit, or ADK, provides the structural framework to orchestrate this automated logic. This architecture relies on three foundational pillars: the model brain for reasoning, tool capabilities for execution, and system instructions to define the operational boundaries. Adopting the ADK framework refocuses engineering effort on the construction of robust, automated evaluation gates. High-fidelity video synthesis requires a multi-model, stateful pipeline to manage the complexity that a single inference step cannot handle. The process begins with an LLM parsing a raw text brief into a structured JSON narrative, which explicitly defines scene timing and camera trajectories. A JSON payload transitions to a static reference image generated by Nano Banana, anchoring the scene's visual identity. Google's VO then expands that locked canvas into a cinematic sequence, simultaneously synthesizing a synchronized audio track. It prevents the visual hallucinations that occur in uncontrolled models. Locking the initial canvas provides structural control, but the system requires programmatic validation to verify the accuracy of the final motion and audio. Orchestrating generative media reveals a challenge. Aesthetic quality cannot be measured by standard programmatic unit tests. Deterministic pixel filters are effective for basic checks, but they lack the sophistication to detect temporal drift or misalignment with the intended narrative. This schematic represents the first objective gate, the SigLIP metric. It independently processes text tokens and image patches to compute a similarity score between 0 and 1 in a shared vector space. SigLIP provides a fast mathematical alignment filter, though it cannot reason about specific structural elements. Structural verification falls to Google's Gecko framework, decomposing the prompt into discrete verification nodes, checking for specific visual elements through a Boolean logic tree. While mathematical alignment and structural verification provide a necessary defense against errors, they remain insufficient for grading subjective brand constraints. Subjective evaluation requires an LLM-as-a-judge architecture to act as the final gate in the automated stack. A multimodal model critiques the asset against specific criteria, including temporal consistency, motion coherence, and the accuracy of the narration. The judge applies 4 design principles: evaluating visual contrast, checking for repetition, ensuring proper alignment, and spatial proximity. This tool outputs a numerical score along with qualitative text feedback that identifies exactly why an asset failed to meet the quality bar. Transforming subjective design failures into actionable JSON feedback enables the system to attempt a targeted self-correction. The central model brain manages the workflow, routing execution between planning, generation, and evaluation tools. Strict pedantic JSON schemas regulate these handoffs, ensuring exact parameter boundaries and preventing any conversational drift. An in-memory runner persists the complete execution state, maintaining a record of quality scores and local files throughout the iterative process. Combining rigid data contracts with a stateful runner transforms a general LLM into a deterministic pipeline controller. A simulated failure demonstrates the system's autonomy. By injecting a corrupted audio script into the pipeline, we can observe how the agent reacts to a validation error. The agent generates the video asset as instructed, passing the file to the LLM as a judge for critique. The judge flags the narration mismatch, dropping the score to low passing and identifying an audio failure. The agent analyzes this feedback, isolates the audio error, and deliberately bypasses the computationally expensive image regeneration step. The agent loops back to the video synthesis stage, injects the corrected audio parameters, and generates a compliant final asset. Autonomy in this system manifests as the programmatic isolation of failure types and the execution of targeted retries, all occurring without human intervention. To manage the complex multi-agent state machines we have discussed, deployment has evolved toward natural language abstraction using the Gemini CLI, a development style referred to as vibe coding. Engineers define agent skills using modular markdown blueprints. This single natural language command then scaffolds the directory structure and generates the underlying code for the ADK architecture. The CLI compiler ingests these blueprints to automatically configure the models and tools required for the media pipeline. This abstraction allows engineers to focus on high-level architectural logic, while the CLI handles the boilerplate Python implementation. This architectural shift marks an evolution from single-shot prompting to the deployment of stateful, multimodal evaluation pipelines. Decoupling the reasoning brain from its tools using strict data contracts remains the essential requirement for reliable automation. The ultimate competitive moat in enterprise media is the engineering rigor of the automated self-correction loops, effectively separating value from foundational models.